Hi everybody, it's Unit 10, Chapter 12, and this is Spectroscopy Part 1. So, spectroscopy is an analysis technique that helps us know what is in our molecule. Alright, so there's a technique called nuclear magnetic resonance spectroscopy, also known as NMR, and what you find out from that is the carbon skeleton, if you do a carbon NMR, and you can also find out the kinds of hydrogens that are in the molecule. Infrared spectroscopy uses electromagnetic radiation to tell you the presence of functional groups. Ultraviolet visible light spectroscopy helps to know a lot about pi electrons, so double bonds and triple bonds. And then mass spectrometry, spectrometry is not really a spectroscopy technique. It's a different kind of analysis technique, and you can find out the molecular weight of your molecule and the formula of your molecule, and by doing that. So, electromagnetic radiation runs from highest energy gamma radiation to lowest energy radio frequencies, and NMR uses some of these and some of that nuclear stuff, and then the infrared uses that, and then the UV uses that. Okay, so electromagnetic radiation is a type of energy that's absorbed in all these different techniques by molecules or by parts of molecules, and then that will cause something to happen to the molecule. Either it'll cause bonds to vibrate, or it will cause nuclei to flip. Okay, so here are the three techniques that use this electromagnetic radiation to help analyze molecules. All right, so not every element, not every atom does this, but hydrogen and carbon do. Hydrogen 1 and carbon 13, which is not, most carbon is carbon 12, but the isotopes of carbon 13 have this, have the ability for their nuclei to be affected by magnetic fields. Infrared spectroscopy uses infrared section of the electromagnetic spectrum to cause my molecules to vibrate in different ways. And then UV uses the UV visible light to talk about two different electron energy states. Okay, so this is a schematic, a generic schematic of what happens in an NMR. Okay, so there's a source of energy, and that source of energy is run through the molecule, and there's a magnetic field in the sample, and then signals from the sample are detected. Okay, here's the detector. Kind of looks like an eye, but it's not. See, look up. Anyway, all right, so NMR spectroscopy, we call it nuclear magnetic resonance spectroscopy. You know it better as MRI, magnetic resonance imaging. It's a technique used to do chemicals, but it's also a technique used to see human body. Okay, so if there's no magnetic field, the nuclei of a molecule, all the nuclei have a spin state of positive 1/2 or negative 1/2. It's just they can only have two, and they call it 1/2 or negative 1/2, and they're random. They're all random. But when you apply a magnetic field, the nuclei will either align with or against the applied field, and then they can also flip when you pulse that magnetic field. So, oh look, random nuclei. So there's a positive charge. That's the nucleus, and look how random they are. But then you apply a magnetic field, and they line up and either spin one direction or the other. You pulse that magnetic field, and they flip. Okay. So when the magnetic field is applied, then the energy can be used to flip the spin of a nucleus from the lower energy state to a higher energy spin state, and it depends on shielding of the nucleus from the applied field. What shields the nucleus are electrons, and so if those electron density is pulled away, then it's less shielded. If it's there's no electron density pulled away, then it's more shielded. Okay, so here we go. You put your sample into the machine in a clear tube. All right, so you have to put it in a liquid in a clear tube, and then there's all these coils, and there's a magnetic field, and then they pulse the magnetic field, and they get a signal. I'm really, really simplifying it, but I just want you to know what happens. Okay, so what does that machine look like? Well, here's what it looks like if you're using a chemical in a tube. Here's a little tube that you put inside there. Okay, here's what it looks like if you're getting an MRI, if you're the sample. So here's a person lying in the machine. Okay, so it's really the same kind of machine, it's just on a larger scale, and there's some other different kinds of techniques of printing out or detecting the information. Okay, so we're first going to talk about hydrogen nuclear magnetic resonance spectroscopy. So this is telling us all about the kinds of hydrogens in your molecule. So what can you learn from hydrogen NMR? You can, from how many signals there are, that tells you how many different kinds of protons are present. So how many hydrogen atoms there are in your molecule that are unique, okay? Meaning that have a different chemical environment. So how many chemically different hydrogens are in your molecule. It also tells you, you can use this as only for hydrogen NMR, the height of the peaks tells you the relative ratios of the hydrogens. It says protons, it always means hydrogens, okay? And then the pattern by which the splitting pattern happens tells you the number of protons or the number of hydrogens within 2 or 3 bonds of the hydrogen giving the signal. And we're going to use what's called the N+1 rule to help us figure out the number of peaks, or what the number of peaks means. All right, so let's look at an NMR. Okay, so this is a hydrogen NMR of this molecule. It's got 1 carbon, 1 hydrogen, and 3 chlorines on that carbon. Okay, so the signal is at a higher number, so that's a downfield shift. Okay, and the higher the shift, the less shielded the hydrogen is. Okay, so what would cause that, right? And so there's only 1 hydrogen in this molecule, so we only get 1 peak. It's got no neighbors, so it's not going to split. And so if we found this molecule and then we put it in an NMR, then we'd be like, oh, there's 1 hydrogen in this molecule. And then chemically we could analyze that there's also chlorine and carbon. Okay. All right, so what causes the shift? So there's 2 kinds of hydrogens. This is not the same molecule we just saw. This is a different molecule. So this molecule has 3 hydrogens on the methyl, right? And then 1 hydrogen on this carbon with the 2 chlorines. Okay. So the hydrogen that's on the carbon with the 2 chlorines will be shifted further downfield, and so this would show up at a peak at a higher number on the y-axis, on the x-axis, sorry, okay, because it is deshielded. So these chlorine atoms will be pulling hydrogen's electrons sort of away from hydrogen, and so the hydrogen's not shielded by its electrons, and so it can shift to a higher number on the spectrograph, okay? These 3 hydrogens would have a separate peak, so there'd be 2 peaks for this molecule. This hydrogen would have a peak, and it would be further downfield at a higher number. These 3 hydrogens would all give the same signal because they're all chemically equivalent. There's no difference between any of the hydrogens and any of the other ones. Are all bonded to this carbon, which is bonded to that carbon, which has 2 chlorines and a hydrogen on it. So these 3 hydrogens would all give the same exact signal, and they would not be as far downfield because they have more shielding because their electrons stay closer to them because they're further away from the chlorines. Okay, so the carbon with the chlorine is, the hydrogen on the carbon with the chlorine is deshielded because the chlorines are pulling electrons away. And so that the signal will be at a higher field, which means higher number. Higher number. Okay. The hydrogens on the methyl will be shielded by each other's electrons, so then it will be at a lower number. That peak would show up at a lower number. Okay, so now we're going to look at some more. So here's a molecule. It's NCCH2OCH3. All right, so we have an ether going on. We have a cyanide or nitrile in there. All right, so there's green hydrogens and there's pink hydrogens. So the green hydrogens are chemically equivalent to each other because their environment is exactly the same as each other. So they will give out one signal. So we'll get a signal from them. Let me use purple. We'll get a signal from them, and we'll get a signal from those hydrogens. And all three of those hydrogens will give out the same exact signal because they're chemically equivalent to each other. You wouldn't be able to tell them apart. They're all on the same carbon, which is on an O, which is so there's two kinds of hydrogens in this molecule, and there's three of the pink ones and two of the green ones. Okay, and so we get a peak for the pink ones and a peak for the green ones, and then the pink ones are a 3-to-2 ratio, so that tells you that there's 3 of those for every 2 of those. So it's a 3-to-2 ratio, and you can tell that by the height of the peaks. All right, and then the green ones are shifted further downfield because you got a nitrogen and some electrons pulling that way, and then you also have an oxygen pulling electrons away. But yes, you have an oxygen pulling electrons away from there, but this one has this hydrogen's, its electrons are getting pulled in 2 directions, so it's further downfield. Okay, so what did we find out from this printout? Well, the green ones are further downfield because they're closer to electronegative atoms, so they're deshielded. There's a height of 2 for that and a height of 3 for the other one, so the number of hydrogens that are making this signal are 2 of them, and there's 3 hydrogens making that signal. Okay, let's look at the next one. All right, so this is a spectrograph. Don't look at these things. Don't look at those for now. So we're looking at this tall pink and this short gray. All right, so there's one kind of hydrogen on this carbon, and then there's a different kind of hydrogen on this carbon, and there's 3 of them. So these 3 same hydrogens will be giving out the same signal because they're chemically the same. This one hydrogen will give out a different signal because it's in a different environment. It's got 2 chlorines pretty close, and this one, these 3 hydrogens don't have chlorines that close. Okay, so which one is going to shift further downfield because it's deshielded? This hydrogen will shift further downfield because it's closer to chlorine atoms. So this signal is coming from that hydrogen. The pink signal is coming from all 3 of those hydrogens together, and you can see it's about a 3-to-1 ratio. All right, a 3-to-1 ratio. So the height of the integrations tells you how many, the ratio of those kind of hydrogens to the other kind of hydrogens. So there's 3 giving off that signal, and there's 1 giving off that signal. Now, what they did is they took this signal and then they blew it up. Okay, so this is just a closer look. A closer look. All right, so in this closer look, we see that there's 1, 2, 3, 4 peaks. So this signal is coming from 1 hydrogen, but it's split into 4 peaks. So that's called the splitting pattern. When there's 4 peaks, it's called a quartet. Quartet, because there's 4 peaks. 4 peaks in this signal. All right, so what causes the 4 peaks? Neighbors cause hydrogen's signals to split. So this gray hydrogen has 3 hydrogen neighbors that are interfering with its signal, all right? Because it's a magnetic field, and these hydrogens are also producing a magnetic field, and so because they're spinning, and so it's causing the splitting of its neighbor. Okay, so neighbors cause a split, and it's n+1. So we have 3 neighbors plus 1 gives us 4 peaks. 4 peaks. All right, 3 neighbors plus 1 gives 4 peaks. So gray hydrogen splits into a quartet because it's got 3 neighbors, and so its signal gets split into 4 peaks. All right. You could also look at 1, 2, 3 valleys makes 4 peaks. So 3 neighbors makes 4 peaks. All right, pink hydrogen. The 3 hydrogens that are pink are giving off the same exact signal, and we tell that by the height of it. All right. Now, do those 3 hydrogens have any neighbors that are going to make up split? So here's a zoom in, zoom in, right? And what you see is that the signal coming from the 3 hydrogens is split into 2 peaks. So this is called a doublet. A doublet. And why is it a doublet? Because there's 1 neighbor plus 1, n plus 1 equals 2, and so we get a doublet. So pink hydrogens are giving off the same signal. There's 3 of them. That's why it's a height of 3, integration of 3. And they have one neighbor. That neighbor will cause it to split into 2 peaks. All right. So the splitting pattern tells you how many nearest neighbors. All right. So if you want to know how many nearest neighbors, you take the pattern in -1. Okay. And then the height of the signal tells you how many hydrogens relative to the other kinds of hydrogens. And the shift tells you how close they are to electronegative elements. Okay, this is talking about the splitting patterns and why the neighbors, so the neighbors are also spinning, and you're also in a magnetic field, so the neighbors can flip. If there's 3 neighbors, they can be this way, they can be that way, they can be this way, this way, this way, this way, this way, this way, so they're going to get 4 peaks. So 3 neighbors, number of neighbors, number of neighboring hydrogens, H's plus 1 equals peaks. And that's the splitting pattern. Okay. All right. We have some hydrogen in this molecule. Now, pink hydrogens are all chemically equivalent. You can't tell them apart. They all have the same, they're all going to give the same signal because they're identical to each other. And so that's the tau signal here. So this is a 3. And then yellow hydrogen is different than gray hydrogen. You might be saying to yourself, no, look, it's a CH and a CH. You're right, it's a CH. But the yellow hydrogen is closer to an O, all right? But gray hydrogen is closer to some chlorines. So gray hydrogen has a different environment than yellow hydrogen. So there's 3 unique hydrogens in this molecule, all right? And then the one kind of hydrogen, we'll call it A, has an integration of 3. Yellow hydrogen we'll call B. Gray hydrogen we'll call C. So we have 3 different hydrogens. So this is A, this is B, and this is C. C is furthest downfield because it's closer to chlorine. So it's de-shielded, and so the electrons are being pulled away, and it gets shifted to a higher number. Okay, this is zoomed in. Zoom. All right, so we take this signal, we zoom in, and we notice it's got 2 peaks. That's called the doublet. Why does it have a doublet? Well, it's got hydrogen close enough to mess with its signal. It's got 1 neighbor. So 1 hydrogen plus 1. So n number of neighbors plus 1 is 2, so it turns into a doublet. Okay, same with the yellow hydrogen. Yellow hydrogen, zoom in, we see it's a doublet. Okay, that's because it's got a nosy neighbor who's messing with its signal, and then we got 1 hydrogen, 1 neighbor plus 1 gives us 2 for a doublet. Another doublet. Okay, why does pink hydrogen have a singlet? Singlet. Why? Well, it's because there's no hydrogens close enough within 3 bonds. Okay, so if we count this hydrogen, there's 1 bond, 2 bond, and there's a hydrogen. So within 3 bonds, there's another hydrogen. These hydrogens, they're all spread out like this, but you have to go 1, 2, 3, 4, 5. So the hydrogens aren't close enough neighbors to split them. Okay. All right, that was hydrogen NMR. Now we're going to talk about carbon NMR. Carbon NMR, carbon still has a carbon-13 is one of the ones that has the effect of this magnetic field on it. And organic molecules have carbon, and so they're going to have carbon-13. Okay, so you can get some good quality carbon NMRs using Fourier transfer techniques. I'm not going to go into that. But anyway, so carbon-13 signals are usually spread out more, and they don't couple. Carbons don't split their carbon neighbors, so they come out as singlets. All right, so carbon-13 NMR is easier to interpret than hydrogen because each peak is a unique carbon. So look, it's a carbon NMR. All right, and we have 1, 2, 3, 4, 5 peaks. You might be wondering what this is. This is a solvent, and it's like just a comparison, something to compare to. So, and it's really far downfield because it's got chlorines on it. And yeah, okay. So the molecule we're looking at is 1, 2, 3, 4, 5 carbons. And so here's our molecule. It looks like looks like a pentane, but it's a 1-chloropentane. 1-chloropentane. All right. So why it's a CH2, 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 CH2. You're probably saying to yourself, all those carbons are the same, but they're not, because this carbon is right bonded to a chlorine. This carbon is next to a carbon that's bonded to a chlorine, so that's different. And then this carbon is bonded to a carbon that's bonded to a carbon with a chlorine. This carbon, the chlorine's far away and it's got 3 H's on it. Okay, this carbon has 2 H's and is bonded to a CH3, but then if you go that way, it's got 2 carbons and 3 carbons and a chlorine. So wow, all of these are unique. All right, and now let's figure out where they are on the field. Okay, so this carbon has its electrons being pulled towards chlorine. So this is going to be 1, and it's going to be this peak, which is shifted downfield. Okay, this is 2, carbon 3 is right here, carbon 4 is right here, carbon 5 is right here. Okay, so there's 5 peaks, 5 carbons. The height of them does not mean anything, okay? You cannot integrate, so no integration. It can't tell you how many of that kind. That doesn't work for carbon NMR, for carbon 13 NMR. Okay, that was only for hydrogen NMR. Okay, so we have a spectrum. All right, so here's our solvent. We ignore that peak. So it looks like we have 1, 2, 3, 4, 5, 6, 7 peaks. So that means we have 7 chemically different carbons who have different environments. All right, so let's count them. Okay, so here's a carbon. All right, here's another one that's 2, 3, 4, 5, 6, 7. So there are 7 carbons and there's 7 peaks. Now you might be saying to yourself, this is a CH, that's a CH, that's a CH, and that's a CH. But because of their environment, they are not equivalent carbons to each other. Okay, this carbon is bonded to an O. That's going to probably be this one over here, right? Because it's furthest downfield. So we'll just put a 1 there. So this is probably carbon 1 because it's shifted that far downfield. All right. Then there's these other carbons, but I am not going to go ahead and, I mean, this probably, well, this could be the methyl, or this could be this one, or this one. All right. So let's call this carbon 7. Probably that's carbon 7 because it's furthest away from the O, which is moving things downfield. So, all right. So there's 7 lines, 7 unique carbons, and the further they are downfield, the closer they are to an electronegative atom. Okay, so 7 unique carbons. Okay, this one, we have some color coding to help us. All right. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons in this molecule. But are any chemically identical? All right. So this one's different. It has 3 H's on it. This one's a CH2, but it's on a CH3, and then there's a chain this way. This one's the third one, and it's got an ethyl that way, and it's getting closer, so this is different. So we have unique, I'm just going to label them this way, A, B, C, D. This carbon's unique because it's bonded to an O, F. Now, here's where we get similar. This is a G carbon, and that's a G carbon, because they both have exactly the same chemical environment. They're off of a benzene ring, in a benzene ring, off a branch. All right, this is a unique carbon here, but it's the same as that carbon. And then there's, we'll call this carbon I. So A, B, C, D, E, F, G, H, I. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. There should be 9 peaks on this. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And there's 9 peaks because there's 9 unique carbons. So carbons H and G are going to give off the same exact signal because they have the same exact carbon chemistry. Like they look exactly identical. They're going to be giving off the same signal. Okay. So here's CO. Why is this one so far downfield? Because this carbon is on the electronegative, bonded to the electronegative oxygen. Okay. This is the carbon with no H's on it. All right, so that's right here. It's pretty close to the C double bond O, and it's in a benzene ring too. All right, so then we have CH, which probably are G. All right, and then we have other CHs. This is probably H, and then this is probably I. Okay, so this is carbon E. This is carbon F. This is carbons G. This is carbon's H, and that's probably carbon I. Okay, now these carbons are way upfield because they're not as close to the oxygen. All right. So this is carbon A because it's a CH3, that's easy. But this is probably B, C, D because they're shifting more downfield as they get towards the oxygen. Okay, so carbons in a benzene ring are de-shielded. Okay, so they're further downfield than carbons in a chain. All right, so 9 unique carbons, A, B, C, D, E, F, G, H, I. You see all the signals, 1, 2, 3, 4, 6, 7, 8, 9. All right, you know where they're shifting. So we learn a lot about that molecule by looking at the carbon NMR. Okay, now, talked about hydrogen NMR, we talked about carbon NMR. You can take a carbon NMR and couple it. That means like put it together with a hydrogen NMR. Okay, and so then what happens to the carbon signal does an N+1 for the H's on the C. H's on the carbon will split the carbon signal to N+1. All right, so I'm going to look at some ones that we already looked at, and we're going to see what they would split. So this is the one we just did, and then I'm going to call this A, B, C, D, E, F. Ooh, looks familiar. G, H, and I. All right, so let's look at carbon E. If we coupled this with the hydrogen NMR, this would not split. This would stay singlet because there's no hydrogens on that. Okay, this would also stay a singlet because no H's. No H. All right, this carbon right here, this signal coming from the carbon has one hydrogen on it. Okay, so if we coupled it, then what would this turn into? Well, this carbon has H, so there's one H plus one. It would turn into a doublet when it was coupled with hydrogen NMR. Okay, and so this one would turn into a doublet and this one. So these peaks would all be doublets if you coupled this NMR with a hydrogen NMR. What about this one? Well, this carbon has two H's on it. All right, so 2 H's plus 1 gives us 3. So this would turn into a triplet if we coupled this carbon NMR with hydrogen NMR. A triplet there, a triplet here. What would happen to this one? Well, it's got 3 H's plus 1. This would turn into a quartet. So you can actually tell how many hydrogens are on each carbon in a carbon NMR if you couple it. Okay, so we looked at this one already. I don't remember what I numbered them. I might have numbered them, but I'm going to call them A, B, C, D, E. They're all unique, so we have 5 signals. All right, we said this was signal A, B, C, D, E. All right, so this is a carbon NMR. You only see one line for every carbon. Those are the unique carbons. Now, if we couple this carbon NMR with a hydrogen NMR, then we could tell how many hydrogens are on a carbon by the splitting pattern. So carbon A has 2 hydrogens plus 1. It would turn into a triplet. All right. This would also turn into a triplet. This would turn into a triplet. That would turn into a triplet. Letter E would not turn into a triplet because this carbon signal, so this signal over here, signal E, would be 3 hydrogens plus 1, 4, so it would turn into a quartet. So the signal would split if we coupled this with the hydrogen NMR. E would turn into a quartet. All right, we looked at this one already, and we said it had A, B, C, D, E, F, G. We didn't say that. I'm just labeling them now, but we need 1, 2, 3, 4, 5, 6, 7 signals. 1, 2, 3, 4, 5, 6, 7 signals, right? So then carbon A would probably be down here. This would be A, and this would be a singlet. Why a singlet? There are no hydrogens on this carbon. B, if we coupled it with hydrogen, would be a doublet. Why a doublet? Because it has 1 hydrogen. E would be a doublet if we coupled. So if we took this carbon NMR and then we coupled it with the hydrogen NMR, then the number of hydrogens would split the carbon signal into N+1. This would be doublet. I'm supposed to put D for doublet. G would turn into D for doublet. C would stay singlet. Singlet. But what would D turn into? Well, the carbon signal coupled with the hydrogens on it would be 3 hydrogens plus 1. It would turn into a quartet. Quartet. Okay, so I think I covered everything.